We're doing the structures now. Go back now. Or do you just not keep drawing?
All right. If we finish something here. Let's get going. So I have some direction fields to kind of go over. So the idea here, we're going to talk about briefly, somewhat briefly, is how you kind of graph the eigenlines and or the null lines in a direction field without knowing the system of equations. So here's this thing we're going to look at. Here's our direction field. And yes, I don't have copies of this one for you all, but I do have copies of the next ones for you all. So for this one here, here's what I'm going to write down over here. To find the eigenlines, now I will point out, you can only find the eigenlines if your system has real eigenvalues. If your system has complex eigenvalues, you can't find them. There aren't any lines that point in towards the origin or away from the origin directly. So that's not always something you can do. This one we certainly can. So for this one, the eigenlines, well, I can see that these arrows all point exactly away from the origin, right? It's not like kind of slanting in. It's exactly that and that, which looks like the line y equals x, and it is. So one of my eigenvectors, not that we need to know this, but this y equals x line here, it's an eigenline. And since the arrows are pointing outward, you know that your eigenvalue is positive. And the eigenvector associated with that would have been the vector 1, 1. And our lambda, whatever that was, would be positive. The eigenlines are always super easy to see. I've made this example really relatively easy to kind of make it easy to graph. In a similar way, we can see that, so I'll point out like this arrow here doesn't lie on an eigenline because it's not pointing towards the origin or away from the origin. Whereas these arrows here along the line y equals negative x are all pointing in towards the origin. So my other eigenline is right there. Y equals negative x. The eigenvector would be the vector 1, negative 1, or negative 1, 1. And the eigenvalue would certainly be negative because all the arrows are pointing in towards the origin instead of away from the origin. Now, again, I'll say we can't always draw the eigenlines because sometimes our solutions have complex eigenvalues, and complex eigenvectors is not something we can graph. At least not in this context. Yeah, the null lines, on the other hand, we can always find whether the solutions are complex or real. The eigenvalues are complex or real. So to find the null lines, you have to look for the curve, usually aligned, but not always if we're dealing with nonlinear systems. We're going to look for the straight line where all of the arrows either point vertically, either up or down, or all point horizontally, left or right. Let's do left, right first. So if I'm looking for arrows that point purely left, right, they look like they're kind of like maybe right about here, right about there, kind of like there. it kind of looks like they're on the line, maybe like y equals 2x. If I go from here up to there, that seems kind of reasonable. And then keep going that way. Right, I feel like I'm hitting arrows that are pretty much purely horizontal. And same thing if I go down this way. Now these graphs aren't perfect because the arrow almost never shows up as horizontal. The way I usually look for is I look for one that's like pointing slightly up and one that's pointing slightly down. So the one between them had to have kind of leveled out. So I'm looking right here specifically. That arrow is pointing slightly down. That arrow is pointing slightly up. So the one between them was probably purely horizontal. So my null line here, I should say my y null line, because we're saying if arrow is purely horizontal, that dy dt is equal to 0. So this is going to be my y null line. I want to use a different color, sorry. Purple, sure. Not, let's just draw arrows at the end, sorry. So here's my y null line, where dy dt is equal to 0. And finally, for our x null line, we're looking for where all the arrows are vertical, or maybe go slightly pointing up right to slightly pointing left right, or slightly pointing down right to slightly pointing down left. So I can see some pretty vertical arrows like right about here-ish. Right, this one's pointing pretty much straight up. This one's pointing slightly to the left. So like from here to here, slightly left, slightly right. So probably something like this. Now, I will point out I am cheating a little bit because I know what the answers are already. I know the lines are the lines y equals 2x and y equals 1/2 x, but we can also see them, right? This line here, yeah, the arrows we're going through are pretty much pointing totally vertically. The same thing to the left. So this is my x null line, where dx dt is equal to 0, and all of my lines either point straight up or straight down. Okay. So given that knowledge, we're now going to look at some examples where we're going to try and pair the graph with the system of equations.
That's what we finished.
Yes, thank you. Good call. Should be enough, probably. Yeah, and there's extras to set to the side. So let's look at these equations here. So the way I'm going to try and make this work is by looking at each equation, finding the null lines for an equation, and then trying to find the graph that has those null lines. That's not the only thing to do, but it's certainly the first thing I would do for any of these. So let's look at the system one here. So for system one, my x null line is going to be negative x plus y equal to 0, or y equal to x. Let's zoom in a bit here. And then my y null line is going to be 2x plus 2y equal to 0, or solving for y equal to negative x. And I'm going to pull out bigger graphs because I have them. So let's see. So let's look at the first option here. Let's look at A and see, okay, does A have those null lines? Well, if I look at the line y equals x, oh yeah, it does look like the line y equals x exactly has arrows that are pointing up and down, which would be my x null line. So yeah, we're looking good here. That is appear. Whoops, let's draw it correctly, James. That's my x null line. Y equals x, which is where dx dt is equal to 0. And looking at y equal to negative x, yeah, that looks good too. So if I look at the line y equals negative x, it certainly seems to have those null lines. Now, here's something we should be extra careful about. Is this the only one that has those null lines? Because maybe there's another one that has the same null lines. So let's double check before we just say that that's the right one. So looking at the rest of our graphs, here's graph B. Definitely the line y equals x, not a null line, right? The arrows do not point purely horizontally or purely vertically along that line. For C, the same thing is true. We look at C, along the line y equals x. No, definitely not. My arrows do not point purely horizontally or purely vertically. Specifically, y equals x should be purely vertically. And for D, same thing is true. Along the line y equals x, I definitely do not have arrows that point purely vertically or purely horizontally. Cool. So system one goes with graph A. I'm going to skip system two and system three because they have something kind of interesting going on. Let's go all the way over to system four. Because that's kind of, so the thing about system two and system three is they actually do have the same null client, so we're gonna have to do more work for them. So let's look at system four here. System four, my X null client. So when I say X null client, we're thinking of arrows that point which way? Vertically, right? Because you're saying the change in X is 0. We know what we're actually doing to find the X null client. We're literally setting dx dt equal to 0. So we're setting what dx dt is equal to 0. So our X null line, which should all be purely vertical lines, should be along the line y equals 2. And similarly here, our Y null line, which consists of purely horizontal lines, we're going to set dy dt, which is equal to x plus 1 equal to 0. I feel like I might have made a mistake there. No, I don't think so. No, I'm just crazy. Okay. And then we're going to get x equal to -1. So we know it's not A. Let's look at all of our other options. So if I look at just the y equals 2 line, so y equals 2, my arrows are definitely not all purely vertical along y equals 2. So that's out. If I look at C along y equals 2, nope, definitely not it. If I look at B along y equals 2, yep, y equals 2 is looking good. Along this line here, all of the arrows are totally vertical. Now you might feel like right about here things look a little dicey, but I'll point out that along this trajectory here, what's happening is you're coming this way and then you're turning around and going purely vertical right there. So it still is totally vertical right there. There's a vertical tangent line, if you will, right there. So we're good to go there. If you look above and below this null line, you should change from going from left to right or from right to left. So same deal over here, right? Right here, this arrow is pointing slightly to the left, and then I go up to the other side, that arrow is pointing slightly to the right. So the arrow between them would be pointing totally vertical. No left or rightness to it. Okay, and then we also should have the null line x equal to -1, and we do. Along the line x equal to -1, we can see that all of the arrows are purely horizontal. And you can just like draw them in between them. For whatever reason, the tool I was using doesn't really like to give you the arrows on the axes. It kind of gives them off the axes. But you can definitely see, oh yeah, those look like they're definitely doing their horizontal thing there. So we would say that B is going to go with system 4. Or system 4 is going to be graph B. Yeah, graph B. All right, so now the last two, which I didn't do this on purpose, but it's not a bad idea to see this last thing here. So for the last two, both of them have the same null clients. The first one, the X null client, is going to be the line y equals 0, which is the x-axis. And we've already said that A was system 1 and B was system 4. And our y null client is going to be the line x equals 0, which is the y-axis. And we can definitely see that for both C and D here, the x-axis, which is y equals 0, definitely is my x null line because all the arrows are totally vertical. And similarly, my y-axis, which is x equal to 0, is my y null line because my change in y is 0. All the lines are horizontal. The same thing is true for this graph as well. My x equals 0 line is my y null line. And my y equals 0 line is my x null line. So how are we going to distinguish between the two of them? Well, this is where we would have to kind of do a more in-depth analysis. We're going to say, well, we can see graphically, and maybe I think we can see that this system looks like a saddle. So you've got things pointing in and then away. Like if you follow a trajectory here, we're going in and away. And then in and away like that. Whereas the C here definitely looks like a spiral, right? We are spiraling around. It might even be a neutral spiral. I can't quite tell based on the arrows. So whichever one of these systems has complex eigenvalues is going to end up going with C. And whichever system has real eigenvalues is going to go with D. So let's figure that out. So let me zoom back out a little bit here. So let me write down system 2 and system 3 here. So system 2 was dx dt equal to 2y and dy dt equal to x. And system 3 was dx dt equal to 2y and dy dt equal to negative x. So very, very similar even in their equations, but definitely have very different graphs. Kind of interesting how they can have the same null lines, very similar equations, but the graphs are very different. Or I should say the direction fields. All right, so let's write the matrix for system 2. The matrix here is going to be, now we have to be careful here. When you're writing out the matrix, it should be whatever your derivative is equal to, coefficient of x, then the coefficient of y. So that should be a 0 for the coefficient of x and a 2 for the coefficient of y. And then for the second equation, dy dt equal to x, that's a 1 for the coefficient of x and a 0 for the coefficient of y. Similar deal over here. In this system 3, our matrix would be the matrix 0, 2, negative 1, 0. So let's find the eigenvalues. Determinant of A minus lambda I is going to be the determinant of negative lambda to 1 negative lambda, which is going to be negative lambda times negative lambda. So lambda squared minus 2 times 1 equals 0. Versus the other one is going to be the determinant of negative lambda to negative 1 negative lambda. And taking the determinant there, that's going to be still negative lambda times negative lambda is lambda squared, but it's going to be minus 2 times negative 1. So we get lambda squared plus 2 equal to 0. One of these equations has real eigenvalues. One of these equations has imaginary eigenvalues. The first equation has the real ones. So here you're going to get lambda equal to plus or minus the square root of 2. Whereas here, you're going to get lambda squared equal to negative 2, which means lambda is going to equal plus or minus the square root of negative 2, which is an imaginary eigenvalue. So it looks like system 2 has to go with the direction field that looks like the saddle, and system 3 has to go with the direction field that looks like the spiral. So going back to our handout here, we're going to say that system 2 goes with graph D, and system 3 goes with graph C. Just to be a little bit more general about things. So I would say if you're ever trying to kind of answer a question like this, you're always trying to look for where are the null lines? What are they? And do they look right? That's most of the way I would solve this. This one is unique. Most of the time, you're not faced with the two systems that have the exact same null lines. And to be fair, honest, I was a mistake on my part. I didn't mean to do it that way. It just kind of happened. I wasn't really paying attention. So then when I printed it out, I was like, oh, these have the same null lines. Well, that'll be good for us to look at. So usually that won't happen though. Questions about any of this? I know it's kind of all over the place here. And again, I don't know if Lee talked about this so much, but I know definitely for Varn's class, there's a homework problem or two where you have to do this kind of thing. So that's one of the main reasons we're actually looking at it. There's a problem where you're given like four direction fields and four systems of equations and asked to figure out which one matches with which one. It's not a bad question. It's a good question. It's just it takes some thought. But I would say you're definitely looking for the null clients. You could do more work, right? For each system, you could actually like find the eigenvalues for each of the four systems and kind of determine what sort of solution it looks like, whether it's a unstable node, a stable node, a saddle, a stable spiral, an unstable spiral, or a neutral spiral, which this last one was a neutral spiral, right? It actually doesn't spiral outwards, it spirals exactly in like a loop. It could be a circle or it could be an oval. Yeah, it definitely doesn't go outward or inward. That's because if you look at your eigenvalue being purely imaginary means you're going to have, when you do like your e to the lambda 1 times t, it's going to be e to the like I root 2 times t. And there isn't going to be a real part like e to the 3t that makes it grow as time goes on, or an e to the negative 3t, which makes it go down to 0 as time goes on. It just has this e to the I root 2t part, which then becomes cosine of root 2 times t plus I sine of root 2 times t, which just gives you the oscillating circulation part. But since we're not growing larger or growing smaller, it just keeps going in the same loop over and over and over again. It's kind of interesting. Okay, so that's most of what I wanted to say about that, I think. All the graphic things. Yeah. Yeah. Yeah, okay. And let's continue talking about solving a system with complex eigenvalues. So I'll point out the reason the last example I did on Wednesday when I graphed it, the reason it didn't look very spirally is because my real part of my eigenvalue was a lot bigger than my imaginary part. My eigenvalue was 3 plus or minus I, and when the real part's a lot bigger, it means it grows much faster than it turns. So that's why I didn't. I played around with it a lot, and I zoomed way out, and like you have this like super weird looking turning thing. But I had to zoom out to like really far out, I think. Anyway, so what I say is it definitely was a spiral, even though it didn't look super spirally because of kind of how little it was turning compared to how fast it was growing. The next example will look more spirally. So let's see, where is my next example? I know I wrote it down somewhere. There we go. So, and we'll solve this one and we'll kind of we'll do it more in the way that instructor Lear taught it, which is a little bit different than how I do it, but not a whole lot. And you do get the same answer. Just he likes to write it a different way. So let's say we want to solve the following system. dx dt is equal to 2x minus 3y. dy dt is equal to 6x minus 4y. And our initial condition is going to be x of 0 is equal to negative 2, y of 0 is equal to positive 1. So if you're asked to solve a system and you're not given an initial condition, it means you don't have to solve for the constants C1 and C2. If you are given an initial condition, it means we do have to solve for those constants. It's usually not too terrible to do though. Either way, we're going to start by doing the usual thing. We're trying to solve dx as a vector, dt equal to the matrix A times the vector x. Or in other words, dx dt dy dt is equal to the matrix 2, negative 3, 6, negative 4 times the solution vector x, y. Or if you prefer, you can say it's x of t, y of t. Usual steps, eigenvalues, eigenvectors, solution, etc. So to find the eigenvalues, determinant of 2 minus lambda, negative 3, 6, negative 4 minus lambda. Let's see, that's going to be 2 minus lambda times negative 4 minus lambda minus negative 3 times 6. Set that equal to 0. Multiply the whole thing out. We're going to get a lambda squared, of course. We're going to get a plus 4 lambda. We're going to get a minus 2 lambda. We're going to get a minus 8 and then a plus 18. So that simplifies down to lambda squared plus 2 lambda plus 10 equal to 0. It does not seem to factor very easily, so we jump straight to the quadratic formula. Or whatever method you prefer to use to find your eigenvalues. So using the quadratic formula, we're going to get lambda equal to -2 plus or minus the square root of 2 squared minus 4 times 1 times 10, all divided by 2. That's going to be -2 plus or minus the square root of, let's see, 4 minus 40 is -36. And then this is going to simplify to -2 plus or minus the square root of -36 is 6i divided by 2. And then we're going to get that our eigenvalues are -1 plus or minus 3i. And even though we haven't talked a lot about stability classification for complex eigenvalues, I'm going to say something right now, and we'll talk about it after this example. So if your eigenvalues are complex, it means we have a spiral. And just like with real eigenvalues, when the real eigenvalues are both negative, it's a stable node. When the real part of your complex eigenvalues is negative, you have a stable spiral. So negativity, whether being negative and real or having a negative real part, leads to stability. If both eigenvalues are positive, you have an unstable node. If both eigenvalues are having a positive real part, you have an unstable spiral. It's going to spiral out because things are going to grow as time goes on. Right? So really, the way the connection I'm thinking of in my mind is that when my eigenvalue is positive, let me write this, sure. So just as a quick aside here, right, when my eigenvalues are positive, well, I'm really thinking about, I'm going to have e to the lambda t. If lambda is positive, that's going to get bigger and bigger and bigger. If lambda is negative, that's going to get smaller and smaller and smaller. So when they're both positive, really, really big. Both positive but complex, really big and oscillating, spiraling. Both negative, get smaller. Negative but complex, smaller with oscillations or spirals. And then finally, when you get one of each, it's a saddle. When it's one positive, one negative, saddle. Right? It goes in one direction, goes out the other direction. We'll write this down too as well, but I just want to kind of say it now as we're going along. So let's find the eigenvector. Singular, right? When it's complex, you just deal with one of them. So we're going to use lambda equal to -1 plus 3i, because we always choose the plus one. I don't know why, we just do. And then to find the eigenvector, we're going to solve a minus lambda I times our eigenvector equal to the 0 vector, which in this case is going to look like my matrix. So 2 minus my eigenvalue, -1 plus 3i, -3, 6, and -4 minus my eigenvalue, -1 plus 3i, times the eigenvector I'm looking for, equal to the 0 vector. So doing it this way, I almost always use the first row. My first row is going to become, let's see, this 2 minus -1 plus 3i simplifies as 2 plus 1, so 3 and a minus 3i. So I end up getting my first equation being 3 minus 3i times x minus 3 times y equal to 0. And I would probably do this as quickly as possible by adding 3y to both sides, so that 3 minus 3i times x equals 3y. And as tempted as I am, I really don't want to say that my eigenvector is x equal to 3 and y equal to 3 minus 3i. If there's a common factor that we can divide both sides by, we should. It's better to divide both sides by 3 and say we have 1 minus I times x equals 1 times y. So that my eigenvector, the x part is equal to 1, the y part is equal to 1 minus I. You could also do it the other way, right? You could also say you're going to solve a times v equal to lambda times v, and then have your matrix 2, -3, 6, -4 times xy equal to -1 plus 3i times xy. And if you use the first equation, it's still going to turn out the same. you're going to get 2x minus 3y equal to negative 1 plus 3i times x. And then you subtract 2x from both sides, you get negative 3y equal to negative 3 plus 3i times x. And if you divide both sides by negative 3, you get y equal to positive 1 minus I times x. Same exact solutions over here. Either way works. I will point out I'm kind of cherry picking my examples, right? I'm trying to show you nice examples so they're not terrible. But a lot of the times your eigenvalues are going to be much worse. Like it might end up being like 3 plus or minus the square root of negative 37 all divided by 2. And then your eigenvalue is terrible. It's 3 plus I root 37 divided by 2. And then when you're jamming that into this equation, doing it this way really does end up looking a little bit better. Because then you can just kind of say, well, I know the coefficient of x, I know the coefficient of y, set the two things equal to each other and don't look back. Whereas if you do it this way, you're having to like add that number to the other side and it's just kind of gross. So I definitely, when my eigenvalues are less nice, I think doing it this way is preferable. But everyone's welcome to their own opinion. Okay, now what? This is where I tend to go a slightly different direction than Lee, but we can do either way. So this juncture, we're going to write our general solution. And let me make sure I try and write it how he did it, just so I can. Yeah, he likes to do it a little bit differently. It's a little bit weird. It's not weird, it's just, okay. So what some people like to do is they then like to write your eigenvector as a real vector plus I times the imaginary part, which is 0, -1. Sorry, that's way too high there, sorry. Which is not necessary, but is totally fine to do. And then we're going to find the solution in the same sort of way we found it last time. Our solution is going to be, and I do like, yeah. So he likes to write the solution as, it's just our e to the lambda t times our vector v. That's where we're starting. And I'm not writing the c because we're going to incorporate it in at the end. So that's going to equal e to the, let's see, my lambda was -1 plus 3i times my vector, which I'm just going to write as v for a minute until I've simplified this more. All right, I know my vector v is right there, but let's just not write all that every time until we need to. So then we're always going to simplify this. This is going to become e to the -t times e to the 3t times I. The I is the part that kind of needs to separate out, so then we can use the cosine sine thing. So then we're going to rewrite this as e to the -t, and this part here, that's where we're going to use the Euler's formula and say that's going to equal cosine of 3t plus I times sine of 3t times our vector v. Which I guess I'll write the vector v. Yeah, I'll write the vector v at this juncture. So my vector v is 1, 1 plus I times 0, -1. Okay. If you choose to do it this way, one nice thing that happens is that the next step is always the same no matter what you do. What do I mean by that? I mean, when you FOIL this out, cosine times this plus cosine times that plus I sine times that plus I sine times that, here's what always happens. You're always going to get, and some people like to call these vectors like u and w or something. I don't really care that much though. So here's what happens. You're going to get cosine times the first vector, cosine of 3t times your first vector. And then you're going to get I sine times I there times your second vector, and I times I is going to be -1. So when you multiply, we already did this. When you multiply that by that, you're going to get minus sine of 3t times the other vector, 0, -1. Plus, the second part's going to be, well, the second part's going to have an I in it. It's going to be e to the -t, of course. The e to the -t has to be there. But then it's going to be cosine of 3t times I times 0, -1. And we're going to pull the I out. So it's cosine of 3t times the second part of the eigenvector. And then it's going to be I sine of 3t times 1, 1. And again, the I gets pulled out in the front. And it always works this way. It's always going to be cosine times your real part of the eigenvector minus sine times your imaginary part of the eigenvector plus I times cosine times the imaginary part of the eigenvector plus sine times the real part of the eigenvector. And it's always the minus here and a plus here. Always, always, always. I don't love doing it this way. It's not my preferred way of doing it, but it works totally fine. Now, the nice thing here that your instructor likes to do, and I do agree with this part, is he then says, cool, we're going to call this G of t. We're going to call, sorry, I actually let me make sure I've got this right. I should be capturing the e to the t there, e to the negative t, sorry. We're going to call that G of t. We're going to call that H of t. And then we're going to say that our solution is x of t equal to C1 times G of t plus C2 times H of t. And we don't split the I here because it's essentially sucked up in this constant here. Kind of like back when we were solving differential equations in 17b, and we kind of had constants that we kind of just kept saying were constants the whole way until we were done with them. Similar kind of idea. All right. Unfortunately here, though, do we really want to find the constants? Finding the constants is terrible. The problem with finding the constants is you actually have to write it up a long way, which is kind of terrible. I don't think we should do that. I don't think it's worth our effort. Yeah. So this is how Lee does it. This is how you should do it on an exam, I would say. The other way I like to think of doing it is just actually multiplying it out. I don't think you have to separate your vector into the two pieces here like that, but you can. It's not terrible. It's just not the way I choose to do it usually. So, yeah.
No, the thing you wrong.
One more time, sorry.
On the top, like you said how there's like the two ways.
Oh yeah, you can either solve that or you can solve this. So right, this way I'm subtracting the eigenvalues from the diagonal spots of the matrix and then saying that times my vector should equal the zero vector. Or the other way is saying my matrix times my eigenvector should equal my eigenvalue times my eigenvector. Both ways result in the same solution. So you can do it either way. I just think for messy eigenvalues, doing it this way is the better way. Okay. So you should definitely practice for those, especially those of you in Lee's. I don't know if Varn is going to cover this or not. It's just I don't know. But for those of you in Lee's class, you definitely should practice doing problems like this because there will almost definitely be one on your next exam. Okay. Let's go ahead and talk a little bit more about classifying systems here. Yeah. Make sure my papers are out of order here. And then I don't think we have time today. Next time we'll talk about solving non-homogeneous systems of linear differential equations where you have an equilibrium that's not the origin. Kind of like which one was it? Our graph, our direction field D. I will just point out, B, not D, B, sorry. System 4, this direction field, I will point out that where the eigenlines cross, where the null lines cross, that's where both differential equations are equal to 0 at the same point. Meaning that's where both equations aren't changing, where we have an equilibrium, right? Where both derivatives are equal to 0. So for this system that I wrote here, which was dx dt equal to y minus 2, and dy dt equal to x plus 1, it should be relatively obvious that, yeah, of course, the origin isn't my equilibrium. If you plug in 0 for x and 0 for y, you don't get these both equal to 0. Negative 1, 2 is my equilibrium. And this is an example of a non-homogeneous system of linear differential equations because we have some extra part added on here that wouldn't end up being in our matrix. But that we'll probably have to wait till Monday to talk about more. Let's go ahead and do the other thing, which is, yeah. So just to make sure we're all on the page I want us to be on. Where'd you go? Where'd you go? So I'm looking for a thing here that I want to make sure I say. You, not you, not you. Yeah, sure. Okay, there we go. So classifying stability based on eigenvalues. So there's basically 6 different things that can happen. So if your eigenvalues are real, we've already talked about this. I'm just going to say it real quick. Haha, real quick. So if both eigenvalues are positive, that means we have an unstable node. So everything is pointing outward. Also called a source. If both eigenvalues are negative, we have a stable node. Also called a sink. And everything points inward. So along the eigenlines, you point straight towards the origin. And again, I'm just drawing generic lines to represent where eigenlines could be. They're not always like this. It's just easy to draw it this way. But then any other initial condition, like if I start here, I'm going to move in towards the origin. Or if I start here, I'm going to move in towards the origin. Just everything is pointing in towards the origin. Whereas for this one, everything is pointing away. And again, the eigenlines kind of act like asymptotes in that they're the direction of strongest attraction or strongest repulsion. So we end up kind of getting closer to them as we move further away or further in. Fine, not finally. Thirdly, if you have one positive and one negative eigenvalue, we have a saddle. Is a saddle stable or unstable? Unstable. But you can get stability if you happen to start with an initial condition that's on the eigenline associated with the negative eigenvalue. But we don't typically say that. So one eigenline is pushing you away from the origin. The other eigenline is pushing you in towards the origin. And if you start anywhere else, like here, you end up going something like that, or something like that, like that. And then we have classifications for complex eigenvalues. I will point out there is one special case we're not talking about, which is if one of the eigenvalues is 0. Neither of your teachers cares about that. But there have been teachers in the past who've been like, oh yeah, I'm gonna give this a tricky one. So if one of the eigenvalues is 0, it's kind of weird. If you're really curious, you can come ask me in office hours about it, and I'm happy to talk about it. So if your eigenvalue is complex, we're going to say that lambda is equal to A plus or minus BI. A is the real part. B is the imaginary part. And all of the classifications are totally based on the value of the real part. Because again, just like here, we're thinking of our solution as x of t equal to c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. If both lambdas are positive, oh yeah, those e to the t's get bigger. If both lambdas are negative, those e to the t's get closer to 0. And if one's positive, one's negative, the positive one gets really, really big and the negative one gets close to 0, so it's still unstable. Whereas here, if that's your eigenvalue, then your solution, as we just saw, looks something like ce to the lambda, which is a plus or minus, so we pick the plus, bi times t times your eigenvector which then ends up looking like, I'm not going to do much more with this, CE to the AT times E to the BT times I. And this part, that just gives you the oscillation, right? Because it's the sine cosine part, which just bounces back and forth between like -1 and 1, or maybe slightly larger numbers, depending on what's going on. But this part here, that's telling us if we're growing or declining. And it's all based on whether A is positive or not. If A is positive, that's going to get bigger. If A is negative, that's going to get smaller. And if A is 0, well, e to the 0 is 1, and you're just going to have pure oscillation, circulation. So that's the whole story. If the real part's positive, we have an unstable spiral. We're spiraling out. So it might look like, something like this. If A is negative, we have a stable spiral. We're spiraling in. It might look something like that. And finally, if A is 0, if your eigenvalue is purely imaginary, there is no real part, we have a neutral spiral, also called a center. I don't really like the name center, but that's what it's also called. So that's where you're just going along the same roughly circular path forever and ever and ever. Like that. Now you might notice I have drawn all my spirals in the clockwise direction. That's not for any good reason other than I don't want you to make any association with clockwise being stable and counterclockwise being unstable. That's not the case. You can have clockwise turning for either stability or instability, counterclockwise turning for either instability or stability. So sometimes the question is, what direction is our thing turning? So let's look at some examples here. So let's say we have the usual setup, dx dt is equal to a times x, and we want to determine the stability of the equilibrium 0, 0. So let's go ahead and get to the good stuff here. So let's say our matrix is 2, -3, 5, -2. So if we're just determining stability, we're not finding solutions, all you need to do is find the eigenvalues. You can even sometimes not even do all that. You really just have to find the signs of the eigenvalues, or if they're complex, the signs of the complex parts. Let me show you what I mean. So here, if I start finding the eigenvalues, determinant of A minus lambda I is going to be determinant of 2 minus lambda, -3, 5, -2 minus lambda. So if I write out my equation, my equation, sorry. I get 2 minus lambda times -2 minus lambda minus -3 times 5. Let's simplify that. We're going to get lambda squared. The lambdas will cancel out. We're going to get a -2 lambda and a +2 lambda. And then finally we get 2 times -2, which is -4, plus 15 equal to 0. So we get lambda squared plus 11 equals 0, or lambda equal to plus or minus I root 11. I have no real part. So that means I have a neutral spiral. But then I would like to know which direction is it turning, right? And again, neutral spiral, my lambda is equal to 0 plus or minus some imaginary part. The real part's 0. How do we find the direction? Well, there is a way to look at your matrix once you know it's a spiral. There's a way to look at either the top right corner or the lower left corner, and based on the sign, it tells you which direction it is. And I never remember which one it is. The way I would encourage you to find the direction of turning, if you're asked to, is to plot 4 points, and draw the directions in those 4 points. So a reminder, this matrix really represents the fact that we have dx dt equal to 2x minus 3y and dy dt equal to 5x minus 2y. So if I'm going to plot what's going on, and the points I would pick are the points 1, 1, 1, negative 1, negative 1, negative 1, and negative 1, 1. So if I plug in 1 for x and 1 for y, my dx dt is going to equal 2 minus 3, and my dy dt is going to equal 5 minus 2. So my vector at that point is pointing 1 left and 3 up. Now I'm not going to go 1 left and 3 up. I'm going to shrink it down so it points in that direction. So I'm going left and up, and I'm going more up than left. 3 times as much, really. So my vector probably points something like that. 1 left and 3 up, or some appropriate fraction of those. Also, a nice thing about picking these 4 points is whatever 1, 1 is doing, negative 1 is doing the opposite thing. So if 1, 1 is pointing left and up, negative 1 is going to be pointing right and down, and more down than right. You can also plug in the numbers. Right? If you plug in negative 1 for x and negative 1 for y, you get negative 2 plus 3, which is 1, and negative 5 plus 2, which is negative 3. Oh yeah, 1, negative 3. Then we'll plug in the other 2 points. So if I plug in, say, 1, negative 1, 2 plus 3 is 5, 1 plus 2 is 7. So my vector is going to look like 5, comma 7. So right and up, but more up, slightly more up, not a lot more. So it's not quite y equals x, it's a little like that. And then you probably could stop at this point. I bet you could all guess which direction is turning right now, but I'm going to finish it off and go that way and say I'm pretty confident this is turning counterclockwise. It definitely looks like it is. So usually with this process, you can figure out which way it's turning that. So we've got something turning counterclockwise, so it's probably going something like that. And that's kind of that's the most understandable way of doing it. It's just to plot a few points until you can kind of say, oh yeah, it's got to be turning this way because of the way the arrows are pointing. So I will point out, just because I can, based on this, if your eigenvalues are complex, you have to start with that supposition. But if they're complex, if the upper right corner is negative, that means you're going counterclockwise. If the upper right corner is positive, it means you're going clockwise. But again, only if you already know your eigenvalues are complex. If you've got some matrix with a negative up there, but it's real eigenvalues, you're not spiraling, so we wouldn't say anything about direction returns. But I never remember it until I actually do an example. And also, I think if you're asked this kind of question on an exam, no one wants you to say, I know because it's a negative there, it's spiraling counterclockwise. They would want you to do something like this. I think it's good to practice this if you're asked what direction the spiral is turning. All right, that's all I got. I have office hours over in CADS. Go enjoy the Whole Earth Festival. And have a lovely weekend. Sure.
First, is this stable or not?
Oh yeah, neutral spiral. I don't think we say is stable. I don't think we really comment on the stability for a neutral spiral. But I should probably look in the textbook to actually see what the textbook says about that.
Good. I do always like make it equal 0, 0.
Well, because we're trying to solve the equation a times, so you're trying to solve the equation a times our eigenvector equal to, so that, but that's the same equation as that. And that 0, that's not just 0, that's the vector 0, 0. That's what that is right there.
It's a vector.
Right, so we usually write 0 with an arrow over it, just like we write v with an arrow over it. Yeah, that's why we're saying equal that.
Okay, thank you.
You're welcome. You're welcome. All right.